Hello, this is mathjazz from Almost Cool. I'm here with episode 2 of Variant Limits. So, let's pick up where we started off today, or this morning. So, I guess one thing to note is that the game saves your data locally. So, when I played this on my laptop yesterday to test it out,
Iosos, a magnificently efficient display of architectural prowess. The power conduits are effortlessly
okay, we
concealed
already
throughout.
heard this.
Every city on this world owes a debt to the pioneering work of those that built the Citadel, and the city
Can't
that
seem
grew
to
up
get rid of
around
it
it.
either.
If there
Anyway,
has ever been
so
a more
the save
perfect
that I
expression of
played
Francis'
yesterday
leadership, I am
didn't
unaware.
show up in the menu.
Interfacing with local systems
I was
reveals
planning on
magnetic
restarting
storms that
anyway, so I
damage
could
civic
record that.
operations significantly.
Even so,
So
the
it
Citadel
was
and
no
the
real
city
problem
of
to me.
Iosos
But now I
alone
have
are the very
the
nexus of
first time I
mathematical
played
civilization.
saved on my
There will be
laptop, and
something
the
to
second
help us
time I
here,
played, which is
I
the
am
one I
certain.
recorded, saved to my desktop. I have not played further than this point, so you will be seeing this from here on out the same way that that I see it. Still no ability to look around. Still no ability to fall off the edge. Okay, so I expect that this region here.
Path to the Citadel is irrevocably damaged. Access impossible.
As the seat of government, the Citadel had outstanding command and control facilities, but the quakes have devastated it. We are fortunate that the distributary is still intact. It's a tracking station for the power flow, the next best thing to the Citadel's consoles.
Confirmed. The distributary remains fully functional.
Come, we will need to cross the city to get there.
So this looks like I should be able to climb up somewhere, but I can't climb higher than I was while they were talking. Notice it's stuck right there. So there's an invisible wall there. But I can go down to whatever was over here. I don't really get the lightning bolt icons over top of the places where I can climb or jump. I think that they mean that there's an action I can perform there. But my first thought when I was playing was that there's some sort of power source. Like, for the bridges, for example, they're the little lightning bolt icons when there are gaps on the bridges, and I thought that it meant that I could power the bridges, but that doesn't work for these trellises here. So, I think that the lightning bolt is supposed to mean that the player can interact with it. Anyway.
Although I have given you substantial instruction in the operations of the Lapis Omnis, I have not discussed how we came to acquire that knowledge. For centuries, the Mantha had lived below ground, unable to escape the darkness. Then, almost overnight, my father was suddenly able to tap the power of the crystals and use them to unite our people. Father never explained how he came to master the Lapis Omnis, how the rise came to pass. What happened back then, in those dark caverns that made the rise possible?
Oh. So, normally when you have a person that unifies everyone else via superior technology, it's a bloody thing. Oh, one thing that's also interesting is you can't re-listen to these. Or at least, I don't know how. You can look at them again, but you can't seem to replay them if you wanted to replay them.
You will need to change the input of energy at the ports. It will allow us to move objects and emitters around the Citadel.
Each port is a branch in the photomaneric power matrix that disperses the energy gathered by the Lapis Sol crystals. Geomagnetic induction incidents have taken many of the emitters off the matrix, disrupting operations.
It seems many things have been thrown out of place by the magnetic storms. With some application, however, you should be able to restore things to their natural order.
Your staff can be used to adjust the flow of energy at a port, changing the behavior of devices connected to that port.
So it looks like is my Y the yes, okay, so my X value gives me is my input. I can control something, and then my Y value is how far this rock moves. So notice I've moved X 10, but the rock has only moved 4 units. So this this appears to be, well, the graph here is of a line. So if we move 10 units in the X and 4 units in the Y, that means that we have a line with slope of 0.4, or I guess that's 2/5. Oh, I need to move the rock so I can go around it. Okay.
Fantastic! You did it.
And what do I need to do here? Oh. Probably make them a staircase. So, H goes up as X goes up, Y goes down as X goes up. So, this will go. Oh, do I need to go through that pipe? Guess I'm supposed to be up here, I think. Like, behind this console. I think I need to get into that pipe. So. Oh no, I just need to form a staircase. Okay. Helps if you read the instructions. So I'm gonna try and get in the pipe anyway. Oh. Ah, this is in the trailer. So we have this function here, which increases from 0 to whatever that x... Oh, I guess the x value is 4. And then I have a sine curve that's been shifted up a little bit. So I want the door to open, so right about there. Oh, okay. Oh, this is cool. So x is a linear function, but our output y's are angular. That's fun. Kids get tripped up on that when they take Calc 2 and have to set up functions that model, like, for example, for work. You might have to build a function that represents how much work is done when you're raising a bucket that's on a rope a certain distance. Now, in a first semester physics class, you might learn how to do that, but you'd usually treat the rope as having no mass. The thing is that with calculus, you can handle the case where the rope has mass, and as you're pulling the rope up, you're rolling up the rope, and now you don't need to, that first foot of rope that you pulled up doesn't move anymore. You don't need to apply work to it to get that to move. And then the next foot doesn't have to move either. So every foot of rope that you're pulling up, once it gets to the top and you've pulled it all the way to the top where you are, it no longer needs to be moved, and the weight that you're lifting gets lighter because the rope gets spooled up. Or there are several problems that are like that, where your input and output variables can be, you might have an input variable that's a distance and an output that's a weight, or an output that's an angle, or an output that's whatever else you're dealing with, and the dimension of the input and the dimension of the output sometimes is confusing to students. So here we have an input dimension that's linear. It's where I put this line on the graph. And I have an output dimension that is angular. Now, let's see. Going back to the problem at hand, I want this function to be... Let's see. Looks like the f function needs to have a height of about here, which looks like half of pi. There are only two places where it has that. That's this point here and this point here. And obviously wheel G is in the wrong position, so let's try the other one. Oh. Interesting. There we go. It's off on the angle a little bit. It's right there. But that's the point that again has half of. Oh, and it has the numerical value here. That's great. So we have half of pi here for f. There are only two places on the graph where it equals half of pi. That was this one and this one. So those are the only two possibilities that work for the left-hand side, and this is the one that also works for the right-hand side, the right-hand wheel here. So now I have a door, and now I can walk through it.
I've not had to open a door like this before, but it should be a manageable problem.
If the slots can be aligned with the tumbler, the door will unlock, permitting access.
Oh, now I don't get to see the doors? That's unfortunate. Okay, so I'm trying to line this and that up, I think. So, I want my G to have an output of 0, so I can check this spot and this spot. And then I also want my F to have an output of 0. So, this is the spot that I need. So that's great. And now we have our door open. I don't want to go over here, even though the game is trying to tell me to go the other way. Yeah. This is a significant problem. My character has been shown to be able to jump several feet, and I should be able to jump off this wall here, and that would bypass one of these, well, it would bypass the whole need to open this gate.
We might need to get a little creative here.
Ports can be set to get energy outputs infinitely close to a value on one side, permitting additional functionality.
Okay, so I need to shoot this emitter at that collector, whatever it needs to be, node, the middle node. So I think that we need to move around about there. This is very sensitive here. I don't know if that worked. Just way too sensitive. Oh, poof, it's gone. Okay, what did I need to do? Okay. So I need to somehow put a limit. Use the input selector, or input slider to select an input. That's not the right thing. Oh. Limit selector. Okay, so not really sure how that works. Oh, it's down here. See, looking at this f of a made me think of this f of x up here. There's an f of a down here. I want the limit. I guess I could have done, this is a limit from the left. Notice the limit from the left is this value, which hits that target. And then we have the limit from the right is going to be along this line and be too far. Has a value of 4. It looks like I need a value of... Sorry, a value of 5? That's definitely a 4 there. Oh no, this is the x value. This is the y value up here. Okay, so we have the limit as x goes to 5 from the right. So as I'm going down to an x equals 5, my y approaches 4. If I do the limit from the left, then as I come up to 5 from the left, my limit is 2, which is what I need to... Oh, and I guess that's what this number is. I didn't understand what that was. This value 2 is my target. I need g of x to be 2, and g of x represents the horizontal distance from this point. So I needed 2 units to the right to hit that. Okay, so that's good. And I can't choose value because my function is never defined to equal to. Notice that it's open and open there, so the function never equals to, but the limit from the left here and the limit from both sides here equals 2. So that's good. I like that. Okay. So now I can walk across this. I guess, did that collector, did that make the bridge down here work? This one? I think it did. Okay. So I have 2 more circular gates. And I have to get both of them to open? Do I have to get those to open too? Let's see. H is blue, F is white, green is G. Line the platform to open the door. Okay, so let's see. Okay, so H controls this little platform and F and G control those doors. So if I want the platform to be at 0 and I want this door to be open, I need to take... I don't want F, I want H. Can I not pick limits on H? I can pick this one. So, H is 0, which puts the platform there. And F is 2 pi. 2 pi is all the way around. I want something that's closer to pi, which is part of the way around. So, this is pi. That's open. Okay, so I need 1 pi, and I need H to be 0. How do I get a limit on H? I want a limit from the left on... Oh, it does it for all functions. Okay. So, notice that the limit from the left on H is 0, because if I am coming up to 9, this is the limit as x goes to 9 of H is 0, which is where I want the platform. And the limit as x goes to 9 from the left is going to be 2 pi. That's up there. I don't want that. But we can switch this scenario, can't we? Let's see. Okay. Let's see. This is where the gate F is open, and H is way off. And then this is the other place where F has opening. Oh, let's take the limit from... There we go. No, because that's going to select up here, because the limit... Fascinating. Well, it looks like we can't open F yet, I don't think. So let's try and open G. So what do we need G to be to open it? G needs to be... Looks like G needs to be pi. So, G equals pi here. Nope. G equals pi about here then. Ah, yes. And then we take the limit from the right. That'll open G. And that also opens F, because as we come down to 6 from the right, the limit of G is pi, which gives us the open door. And the limit of H is 4, which puts the platform at 1, 2, 3, 4 units. So we can go through G. We can't go through F yet, but probably something in G will allow us to change this. So, let's go through G.
Outstanding!
Okay, so this is, we have to get... I guess we have to get all of these to 0 again. So let's see. Put them here. And the value of G is 1, but the limit from the right is 0. So, as we're coming down here, the limit from the right of G is 0. The value and the limit from the right and the limit from the left and the two-sided limit are all 0 for F. So this was a easy one to get. We'll do this one.
I have analyzed this system, and there is no configuration that will allow the wheels to line up to permit access.
Perhaps we don't need them to line up. We could use a phase anomaly to our advantage here.
If an input is supplied to a crystal for which the output energy does not exist, a phase anomaly occurs, and the crystal, and whatever is linked to it, will vanish.
They can be dangerous, but right now it could be useful to us.
So, if we take, I think what they mean is that if we take the limit from the left, where it doesn't exist, it'll, that shouldn't exist, because we're not defined to the left of x equals 0. Oh, let's see. The other option is we can define a two-sided limit. There we go. The limit does not exist because the limit from the right and the limit from the left are different on both wheels. So, by asking for the two-sided limit at 5, which doesn't exist, both of these wheels phase out. Which I guess we did when we were playing before with one of these puzzles.
It's a curious thing about limits, don't you think? That there are cases where they simply cannot exist.
Curiosity not indicated in this case. If a function has different limits when approached from either side, the implied two-sided limit does not exist.
Yes, I know that. But it is still an odd phenomenon. And useful too, since we can use this to trigger phase anomalies to our advantage.
So I can't go through F, which is sad. Oh well. I'm kind of a completionist when it comes to these games. So... I think it's funny that they would build
I don't recommend
teleporters.
it, but it may become necessary to transmaterialize without using a pad.
Safety tolerances will be exceeded when using transmaterialization without pads.
Yes, I didn't say it was safe, but it works.
If an emitter connects with an already powered node, the circuit...
The emitters here are operators. They have 2 crystals rather than 1.
By combining certain crystals in particular configurations, new angles and positions become possible.
That was my point, yes.
Okay. I think that I was supposed to listen to more dialogue to hear what I was going on. Or what was going on, but I guess it's too late now. So, we're trying to figure out... guess we can hit -2 or 3. So... -2 plus 0 is -2, so that'll give us 1 target. Notice how the white line is F, the green line is G, and so what we do when we're computing F plus G is we figure out the height of the point on F, the corresponding height on the curve G, we add those together. So here we get a height of 0 on F, a height of -2 on G, and add them together to get -2 overall. Okay. So, that hit that target. And then the other crystal needs to hit... Oh. This is what they were talking about. Hitting something with a something else. Okay. So we need all of these to read 0. So... the limit here is 0. Value here is 0, also the limit from the right, and the value. And... Let's see. Hey, they light up the side that we're looking at when we say from the right, it lights up this side. Okay, so... Let's see... What we could do... So we could figure out where one of these things is 0 and where the rest of them don't exist. That should line up the lock by creating a phase anomaly. So, let's see. No, I guess phase anomalies don't work on locks. Okay. So let's see, what do we need to line up? We want all of these to equal... Oh. Yeah, we want all of these to equal 0. That gives us this point, which doesn't work for the other two. And no other point. Oh, they don't have to all line up to be 0, they just have to line up with each other. That's fascinating. Didn't realize that. Okay, so we want all of them to have the same value somewhere. And where does that occur? Well, H is the only one that's negative here, and G is negative there, so those aren't going to work. So, let's see. The right-handed limit on G looks like it's the same height as the right-handed limit of F, which looks about the same as the right-handed limit for H, right here. There we go. They all line up even though they're not lined up at 0. Okay. And that got me to... I think that turned on this cable here that's going across this broken region. And then I guess I can go back. Okay. And then we want to hit the other orb over there. Yes, okay, that's what they meant. There's an orange orb on the right side of that archway. I guess the blue ones are for just transporting energy to do something, but the orange ones are for teleporting the player. Okay, so what we do now is we want to get F plus G to equal 3 so I can hit this orb instead of the -2 orb. So, let's see. Again, the same thing, we find the height of F and the height of G and add them. So, this here, the limit from the from the left of G is 1. The limit from the left of F is 2. 1 plus 2 is 3. So I want to move this right here and compute the limit from the left, and that'll hit my target. This is pretty fun. So I guess I don't activate that over. Do I activate this here? Yes. Okay.
Another magnetic storm. As if the solar flares were not worrying enough.
Coronal mass ejections trigger flux transfer, initiating geomagnetic induction currents, dissipating to ground locally.
So I think it was it Einstein or Feynman that said explain things in the simplest terms possible and no simpler. Seems like the receptor needs a refresher on that. Okay, so align the platforms to create paths to the left, right, and center. So, oh, here's a pad, here's a pad, here's a pad. This is F, and that's H, and this is G. And we need to go, I guess we need to go here. We need to go to all 3 of these places? Let's go to here first. So this is going to be H of -2, so we want all of these functions, maybe not the functions, maybe the limits of the functions, but we want all of them to be -2. So, it looks like here is where we want to go. And we want to do a limit from the right, from the left. There we go. This is the left side. And now they all line up here. So now I go to this thing. Okay, so the target is 2, and I'm currently at 0. And if I just hit this one, it'll hit the target. Because my value of G is 0, the value of F is 2. Even though the limit, the two-sided limit of G is 2, the actual value is 0. So that gets my target. And then I have to go across. Okay, so it looks like what I have to do is I need to get both of those two orbs, the blue orbs, lit up, and I have to go over to this platform next to light up the second orb. So, if I want to line up here, this will be, well, probably 2 units to the right. Right now I'm 2 units to the left of center. 2 units to the right of center should line me up. So I need to look at this and say, what do I need? So if I do this and do the limit from the right, that hits 2, which is where I need to be. I need to be here at 2. This hits 4, which is too high. But... here we go. We have 2, and 2, and 2 for my right-handed limits. So now I can run across here. And I can set this. And I want to hit a target of 2. And it looks like... what will work? Oh! Value there is 2. But the value of f is 1. Oh, if I just take the value, f doesn't exist here, so... nah, because that's... yeah, 2 plus something that isn't a number, so that's not going to work. However... this is where we want it. See? F is 3, G is -1, 3 minus 1 is 2. That sets up the correct alignment. Now we want to put these all in the center. This is 0 here. Oh, great. Now we don't want the limit, we just want straight value. I guess we could take the left limit, but now we get to run through here, and the bridge is operable, so we can run across that.
We're making progress.
And I think that with this here, we're gonna have to take a pause and wait for the next episode to see what's down this staircase. So, see you all next time. I hope you're enjoying going through this game, and I hope that you're enjoying learning calculus. Bye!